What looks like a simple metal grill actually requires dozens of accurately formed parts. This workshop is producing large ventilation louver panels, used on buildings and industrial facilities to allow airflow while helping block rain and debris. The process begins with large metal sheets. Workers move the heavy material with lifting equipment before a powerful shear cuts it into smaller blanks of controlled dimensions. The prepared sheets now move to automated cutting equipment. Computer-controlled machines cut long strips and smaller components according to the required panel size. Workers then inspect the edges and remove sharp burrs with handheld grinders. Accurate cutting is important because these pieces will later become repeating louver blades. Even a small dimensional difference would become obvious once dozens of them are assembled side by side. Smaller parts are punched and prepared before the forming stage begins. Workers position each blank beneath mechanical presses that create holes, notches, and connection features in predetermined locations. The machines provide repeatable force, but the operator must keep every piece correctly seated against the guides. These small details later determine how accurately the blades and outer frame fit together. The long metal strips now enter a large press brake. Workers carefully position each strip while the upper tool descends and bends the sheet into a precise angled profile. These formed sections will become the individual louver blades. The angle is important. It must allow air to pass through while overlapping neighboring blades enough to reduce direct entry of rain and debris. More strips are bent one after another, creating a large batch of nearly identical blades. The press brake supplies consistent forming pressure, while workers repeatedly measure, rotate, and reposition the long pieces. Producing uniform angles is essential. If only one blade is bent differently, the spacing of the completed louver can become uneven and affect both appearance and airflow. The formed blades are now arranged inside a supporting frame. Workers position each section at equal spacing and weld the contact points one by one. Welding turns dozens of separate pieces into a rigid panel capable of maintaining its geometry during installation. At this stage, human judgment becomes especially important because the welder must control heat carefully to avoid distorting the thin sheet metal. While the louver section is being completed, workers prepare the heavier outer frame. Metal profiles are measured, cut, and fitted together at the corners. These frame members carry the weight of the entire assembly and provide the mounting surfaces used when the panel is installed in a wall or ventilation opening. Precise corner alignment keeps the finished unit square. Protective film remains on some of the metal surfaces, while the frame components are fitted and joined. Workers use hand tools to adjust corners before welding them permanently. The welded areas are then ground smooth to remove excess material and create cleaner transitions. Machines speed up cutting and grinding, but final fit still depends heavily on the worker checking each joint by eye and by hand. The completed louver section and outer frame now come together. Workers weld and secure the assemblies, then grind the joints to remove rough edges and welding marks. Particular attention is given to the corners and exposed surfaces because these areas will remain visible after installation. This finishing also removes sharp edges that could make transportation and installation more difficult. The finished panel receives a final inspection and surface cleanup. Workers check blade spacing, frame straightness, welds, and overall dimensions before lifting the large unit from the workbench. Although each louver blade is made from relatively thin sheet metal, the repeated folds and rigid outer frame create a surprisingly strong structure. Finally, the completed ventilation panels are moved outside and loaded onto a truck with a forklift. What began as flat metal sheets has become a large architectural ventilation component through cutting, punching, precision bending, welding, grinding, and careful manual fitting. Machines provide the force and repeatability, but skilled workers control the accuracy at almost every stage. How do thousands of soft, absorbent towels begin with nothing more than cones of yarn? In this factory, plain bath towels and custom jacquard towels are produced from yarn through weaving, washing, cutting, sewing, and final packaging. Hundreds of yarn cones are arranged on large creels and guided toward the loom. Keeping each thread under consistent tension is essential before high-speed weaving begins. The yarn now enters large, computerized terry looms. Thousands of warp threads move independently, while the loom repeatedly inserts crosswise weft yarn. Special mechanisms also create the raised loops that give terry towels their soft texture and high absorbency. Jacquard control allows logos, stripes, and decorative patterns to be woven directly into the fabric rather than printed afterward. The continuous towel fabric is wound into enormous rolls as it leaves the loom. Workers remove and inspect these rolls before sending them to the finishing section. At this stage, the fabric already has its basic structure, but the fibers still need additional treatment to improve softness, cleanliness, and absorbency. Large rolls allow hundreds of towels to be processed together instead of individually. The woven fabric now goes through industrial washing and finishing equipment. Large quantities of towel material are fed through machines that remove residues left from yarn production and weaving. Cleaning the fibers helps water penetrate them more easily, which is essential for a towel designed to absorb moisture. Workers monitor each load, while automated equipment handles the heavy fabric continuously. After washing, the long fabric passes through large drying and finishing rollers. Controlled heat removes remaining moisture while the rollers guide the material evenly through the machine. Temperature and fabric tension must be balanced carefully. Excessive heat can make fibers harsh or cause unwanted shrinkage, while uneven tension can distort the woven pattern and final towel dimensions. The finished fabric now reaches automatic cutting and hemming equipment. Machines measure the continuous material, cut it into individual towel lengths, fold the raw edges, and stitch them securely. Automation makes these repetitive operations much faster, but accurate feeding remains critical. If the fabric shifts even slightly, borders and woven designs can become uneven on the finished towel. The finished fabric now reaches automatic cutting and hemming equipment. Machines measure the continuous material, cut it into individual towel lengths, fold the raw edges, and stitch them securely. Automation makes these repetitive operations much faster, but accurate feeding remains critical. If the fabric shifts even slightly, borders and woven designs can become uneven on the finished towel. The completed towels are folded, stacked, counted, and prepared for shipment. Workers compare the finished pieces, organize them by size and color, and seal large stacks inside protective plastic packaging. What began as thousands of individual yarn threads has now become a finished towel through precision weaving, wet finishing, drying, automated cutting, sewing, and careful human inspection. How does a flat sheet of corrugated board become a strong shipping box capable of protecting large products during transport? In this factory, custom cardboard boxes are produced through printing, slotting, cutting, folding, stitching, and die cutting. The process begins with stacks of corrugated sheets, while workers prepare the flexographic printing machine for the next production run. Workers pour printing ink into the machine and mount flexible printing plates onto the large rotating cylinders. These plates carry the logos, handling marks, and product information that will appear on each box. Careful positioning is important because even a small alignment error would repeat across hundreds of sheets. The operator cleans and adjusts the plate surface before production begins. Large corrugated sheets are now fed into the printing and converting line. Powered rollers pull each board through the machine, while the printing cylinders transfer ink onto the outer liner. Corrugated cardboard gets much of its strength from the fluted paper layer trapped between flat liners. The challenge is to print and shape the board without crushing those internal flutes. The printed sheets continue into the slotting and scoring section. Large rotating tools cut slots for the box flaps, while other wheels press controlled crease lines into the board. These creases allow thick, corrugated material to fold accurately without tearing its outer paper layers. The machine produces the cuts repeatedly, while operators watch the sheet position and print alignment. The large blanks are removed from the line and handled manually. Workers fold the board along the newly created score lines and bring the side edges together. Because these boxes are designed for bulky products, the sheets are large and difficult to control alone. Human handling is especially useful here because workers can quickly correct small bends and keep the printed panels properly oriented. The overlapping side seam is now secured with metal staples. A stitching machine drives a row of fasteners through several layers of corrugated board, creating a strong mechanical joint. For large transport cartons, stitching can provide greater resistance to pulling forces than a simple glued seam, especially when the box will carry heavier products. Completed blanks are stacked and moved through the workshop, while another batch of corrugated sheets enters a separate converting machine. Workers feed the sheets one at a time, while rollers guide them through scoring and cutting operations. The machine maintains consistent dimensions, but operators still inspect the finished edges and fold lines because variations in board thickness can affect how cleanly the material forms. The newly processed sheets are collected into large stacks and transferred with material handling equipment. Bundling flat boxes instead of assembling them immediately saves a significant amount of storage and transportation space. Workers align each stack carefully before strapping or moving it, preventing the large sheets from sliding or bending at the corners. Another production line handles smaller box blanks automatically. The sheets pass through rollers that fold and compress the board along predetermined C machines make these repeated folds extremely consistent, while workers collect and organize the finished pieces by size and order. The folded cartons are compressed into neat bundles and moved away from the line. Workers stack the flattened boxes on expandable roller conveyors before transferring them towards storage. Keeping the cartons flat at this stage allows hundreds of boxes to occupy only a fraction of the space they would require if fully assembled. Some box designs require more complicated shapes than straight slots and folds can create, so the corrugated sheets are sent to an automatic die cutting machine. A specially shaped cutting die presses against each sheet, creating precise outlines, tabs, openings, and crease lines in a single cycle. Die cutting makes it possible to produce trays and custom packaging that would be difficult to form accurately with standard rotary cutters. The completed boxes are then stacked for shipment. What began as simple corrugated board has now become custom protective packaging through printing, scoring, slotting, stitching, die cutting, and careful human inspection. From soft towels and ventilation panels to custom cardboard packaging, every process shows how simple materials gain value through precision machines and skilled human control. If you enjoyed these satisfying manufacturing processes, like the video, subscribe to KenTT Machine and tell us which factory process impressed you most.